Honors Chemistry. This is the one and only lesson in a one-lesson unit called Nuclear Reactions. We're just going to go through a brief overview of nuclear reactions and radioactivity. So let's review. There's three basic types of reactions or processes in chemistry. Determine physical reactions, and they determine the state of a substance as either solid, liquid, or gas. So again, solid water is ice, liquid water we just refer to as water, and water vapor we refer to as steam. But all three of them are H2O. So chemically they're the same. It's just what is the state of matter, and that's called physical reactions, are the changes between those states. Chemistry mostly deals with chemical reactions, and that's the rearrangement of atoms to create two new substances. So we can take two hydrogen molecules plus an oxygen molecule and break the hydrogen and oxygen apart and then put them back together so that we have two water molecules. So that's a chemical reaction. It's when elements on the periodic table are arranged and rearranged to form new substances. The subject of this lesson is nuclear reactions. It's really a subject that belongs more to physics than to chemistry, but nuclear reactions are reactions that take place in the nucleus. Remember, the nucleus is the center of an atom. It contains protons and neutrons. Electrons, the third subatomic particle, fly around outside of the nucleus. But if there is actually a change to the nucleus of an atom, that's called a nuclear reaction. So they add or subtract protons or neutrons from the nucleus of an atom. Nuclear reactions convert mass to energy by Einstein's equation E = mc squared. So the universe, the physical universe as we know it, really only consists of two major components or parts. One is mass. That's things that we can hold and weigh and see. Our body has mass. The chair you're sitting in has mass. Your pencil has mass. The sun has mass. Those are all things with mass. Energy is a little more vague what it is. It's something that makes mass either move or change in some way. So if you have a soccer ball sitting on the grass field, there's a soccer ball. Now you kick it through the air. It's the same soccer ball, but now it's moving through the air, so it must have something inside of it that it didn't have when it was just sitting on the grass. And that something is energy. So energy is making that soccer ball move. Similarly, if you took a piece of paper and you lit a match and burned it, it would turn from paper into ashes. That's a chemical reaction. And that's a combustion reaction, and that's also something that energy does. Generally in chemistry, in fact always in chemistry, we're interested in that second kind of energy, how energy can be used to change a substance from one substance to another. But it's all described by this very simple equation Einstein came up with, which is E = mc squared. What that means is that mass times the speed of light squared equals energy. So the speed of light squared is a very large number. It's 9 with 16 zeros behind it. So if you take that very large number and multiply it by even a small amount of mass, you'll get an enormous amount of energy. And that's how atomic bombs work. It's how nuclear power plants can power a city for years and years and years, is because it doesn't take very much mass converted into energy to create a whole lot of energy. If protons are removed in a nuclear reaction, one element will be changed into another. Remember, protons are what give an element its identity, how many protons. So if you change the number of protons, you've changed one element to a different element in doing that. So isotope notation. Isotope notation tells the mass number and atomic number of an isotope. So this slide is a review of a concept that we learned way back in the foundations unit. So if you look at that notation over there, the top number is called the mass number. It tells you two things really. It tells you the total number of protons and neutrons in the nucleus and is measured in atomic mass units. So it tells you the mass of the atom in atomic mass units. Remember, each proton and each neutron is one atomic mass unit. So if you know that there's 238 atomic mass units in that particular atom, then there must be a total of 238 protons and neutrons. So it tells you those two things: how many protons and neutrons, and what the weight or mass of that atom is. The number on the bottom there is called the atomic number, also called the Z number. So maybe you remember this from back a while back, and that tells the total number of protons in the nucleus and identifies the element. Therefore, if you know the total number of protons and neutrons from the mass number, and you know the total number of protons from the atomic number, you can do a subtraction and figure out how many neutrons are in that atom. So the fact that there's 92 protons means it must be uranium. You can't have any other element that has a 92 in that bottom position. The 92 protons identifies the element as uranium. And the uranium atom, another notation you can write, is simply U-238. That means uranium with a mass number of 238. Again, since the periodic table will tell you that it has to have 92 protons, you can tell how many neutrons it would have just by knowing that it's U-238. Okay, radioactivity. It's a word that you've heard before, so now you're going to learn what it is. Radioactivity is when particles or high energy waves are released from the nucleus of an unstable atom. Generally, these are very large atoms like uranium, but they don't have to be. Carbon has radioactive isotopes that are used for dating fossils and ancient relics, and there are smaller atoms that can have radioactive isotopes. It's usually just one isotope of an atom that's radioactive, not every isotope. So there are three kinds of radioactivity. Alpha particles, and that symbol is a Greek letter alpha, basically A for in Greek. So alpha particles consist of 2 protons and 2 neutrons. And if you go and look at your periodic table and look at helium, you'll see that a helium nucleus has 2 protons and 2 neutrons. So an alpha particle is the equivalent of a helium nucleus. It doesn't have any electrons, though. It's just equivalent of the nucleus. Then there's beta particles, and they're high energy electrons emitted, that means released, from the nucleus. So basically it's an electron being fired out from the nucleus. Now you may say, wait a minute, electrons are not in the nucleus. Well, there's a way that the nucleus can produce them, and we're going to see how that is. And then finally there's gamma rays. Gamma rays are high energy electromagnetic waves with no mass. Electromagnetic waves is not a subject, it's a subject you probably or might have touched on in physics, but it's not a subject we're going to really deal with. I'll talk a little bit about it in one of the later slides. But basically all of the energy we get from the sun in the form of light and heat and a lot of other types of waves are electromagnetic waves. So let's look at alpha particles. Alpha particles consist of 2 protons and 2 neutrons. So that diagram over on the right shows a big nucleus, and coming out of it is a little package that has 2 protons in red and 2 neutrons in gray. So that's an alpha particle. So when a uranium atom, which has a Z number, an atomic number of 92, loses an alpha particle, it becomes a thorium atom. That's Z90. So the nuclear equation is, and I want you to learn how to read these nuclear equations, okay? And it's very simple. It's really just arithmetic. So you start off with a uranium atom that has a mass number of 238 and an atomic number of 92. So remember, the mass number is the total number of protons and neutrons, and the atomic number is just the number of protons. So if that uranium-238 loses an alpha particle, it's lost a total of 4 protons and neutrons, 2 protons and 2 neutrons. That's a total of 4. Therefore, the mass number goes down by 4, so it goes from 238 down to 234 after the reaction. Now, the atomic number is how many protons, and we just said that alpha particle has 2 protons. So the nucleus just lost 2 protons. That means the atomic number went from 92 down to 90. Once the atomic number goes from 92 down to 90, it's no longer uranium. Remember, it's the number of protons that determines the identity of the element. So if you look at your periodic table, number 90 is thorium. So you now have a new element, thorium-234, which has to have 90 protons. The other thing that came out of that was the alpha particle, and that's the helium. It's equivalent to a helium nucleus. It didn't come from a helium atom. It came from the nucleus of the uranium, but it's effectively a helium nucleus. It has 2 protons. Helium has to have 2 protons, and a total of 4 particles. So 2 protons, 2 neutrons, that's a total of 4 for the mass number. So notice that the lines on the top and the lines on the bottom have to add up. They have to balance. So this is how you balance a nuclear reaction. It's not using coefficients like we've done before, but you see that 238 on the left side of the arrow equals 234 plus 4 on the right side of the arrow. And 92 on the left side of the arrow equals 90 plus 2 on the right side of the arrow. So that's how you know that your nuclear reaction is balanced. The loss of 2 protons reduces the atomic number from 92 to 90. This changes the element from uranium, that's a Z equals 92 number, to thorium, that's a Z equals 90 number. The loss of 2 protons and 2 neutrons reduces the mass number from 238 down to 234. That's 4 atomic mass units. Each proton, each neutron is 1 atomic mass unit. Put that in first. Rutherford used alpha particles in his gold foil experiment. If you remember way back in about lesson 5 or 6, we talked about that. And he fired the alpha particles at the gold foil, and most of them went through. Some of them curved a little bit, and a few of them, very few of them, but some of them bounced right back at him, which indicated that there was a solid nucleus inside of gold. Okay, so alpha particles are the weakest form of radiation. They can be stopped by a piece of paper. Just a piece of paper will block an alpha particle. Okay, the reason that's in red down there is there's going to be a question on your district final that asks about this is called the penetrability, or the ability of the particles to penetrate. So alpha particles can't even penetrate a piece of paper. Penetrate means to go through. They can't even do that. So a piece of paper will stop an alpha particle. Okay, beta particles are high energy electrons released from the nucleus. So again, you may say, wait a minute, there aren't electrons in the nucleus. Well, we're going to explain how you can get electrons out of the nucleus. So here's a nuclear reaction involving iodine, and it's an iodine atom releasing a beta particle. So you start with iodine, which has to be atomic number 53. That defines iodine, and it has a mass number of 131, which I guess is about another 78, if I'm doing my math right, 78 neutrons. So 53 protons, 78 neutrons will give you 131 protons and neutrons. Okay, so what happens is this. Let me go down and let's go through this on the bottom first. So think of a neutron. Remember, a neutron is neutral. And what a neutron kind of effectively is it's a proton with a positive charge and an electron with a negative charge stuck together. So if you take a positive charge and a negative charge and you stick them together, they neutralize. They have no charge. Positive, negative offset each other. So think of a neutron as a proton attached to an electron. Now, we've always said that protons and neutrons have exactly the same mass. They don't. Neutrons are actually ever so slightly heavier than protons, and that's because they have this little extra bit of mass from the electron. Very small amount. So when the electron flies away, which is what a beta particle is, the neutron becomes a proton. So think about that. You had a neutron, which was a proton and an electron stuck together. The electron flew away. It just flies off into space. It goes off, goes away. So what you have left behind in the nucleus is another proton. So in effect, a neutron was turned into a proton in that process. So this increases the atomic number by 1 and changes iodine into xenon. Because remember, if you change the number of protons, you have a different number of protons, you have a different element. It's the protons that define the element. So since the electron has almost no mass, the mass number does not change. So it has such a small mass, we don't change the mass number. So look up above there. You have iodine with 53 protons and 131 protons and neutrons. After the reaction, that electron flies away. That's that E way over there on the right with a 0 because it has no mass, and it has a -1 charge. We know that electrons have a -1 charge. So when it flies away, you turned a neutron into a proton. That means your mass did not change. It's still 131 for the xenon. However, you added a proton. You took away a neutron and you added a proton, so the atomic number goes from 53 up to 54, and that's what changes the iodine into the noble gas that's right next to it, which is xenon. So let me say that again. You start off with 131 protons and neutrons. 53 of them are protons. Now you turn one of the neutrons into a proton. So now you have 54 protons. That means you now have a new element called xenon. Since a proton and a neutron weigh essentially the same, you haven't changed the mass of the new atom. The new atom has the same mass as the old atom, 131. So that's what happens in a beta decay. It's called beta decay reaction. Okay? Add one proton, subtract one neutron, mass stays the same, mass number stays the same, but you have an extra proton, which means you now have a new element, xenon instead of iodine. Okay, now beta particles can penetrate a bit more than alpha particles. They can actually penetrate several millimeters into your skin. They don't go all the way through your body, but they can go into your skin, and that can cause problems if you're exposed to too many of them. Okay, next we have gamma rays, and gamma rays are high energy electromagnetic waves. They're not particles, so they don't have mass and they don't have charge. Electromagnetic waves are the type of energy that we receive from the sun. And there are 6 kinds of electromagnetic waves. In order from least to most energetic, they are radio waves. These transmit radio, television, and cell phone signals. Infrared waves. These carry heat. Visible light, that's what we can actually see with our eyes. And that's just a very small fraction of the types of electromagnetic waves, or the kinds that we can actually see. Ultraviolet light, X-rays, these are used by doctors and dentists. They can penetrate your skin but not your bone. That's why when they take an X-ray, they can see what your teeth look like or what your bones look like if you break a bone, things like that. And finally, the most energetic is the one we're talking about. Those are gamma rays, and those can go all the way through your body. So gamma rays can penetrate through your body, and they can penetrate through concrete. One thing that will stop them is a thick block of lead. Lead will stop gamma rays. Okay, there are 2 types of nuclear reactions we're going to talk about. There are 2 major types, and we're going to talk about both of those. So the first is called nuclear fission. Fissure means to split something. So nuclear fission occurs when an atom is split by a neutron. Energy is released in a fission reaction. Okay, so let's look at that reaction. You have a uranium-235 atom there. So it has 92 protons, that makes it uranium, and it has a total of 235 protons plus neutrons. And uranium is the largest natural element that is stable, that doesn't completely fall apart naturally. Anything bigger than uranium falls apart. So what that means is that uranium is pretty close to falling apart. It's very unstable. So if you fire a neutron into a uranium nucleus, it's going to break it apart. So what does it break into? It breaks into barium, which has 56 protons and a mass number of 139, and it breaks into krypton, which has 36 protons and 95, a mass number of 95 protons and neutrons. What it also does is releases 2 neutrons. So that's the 2 over on the right-hand side. You have neutrons. They have a mass of 1. They have no charge to them because neutrons don't have a charge. So you get 2 neutrons out. Now those 2 neutrons that are flying out on the right side, if there's enough other atoms of uranium nearby, then they will strike those atoms and cause those nuclei to split. And each of those nuclei will release a total of two electrons, which is a total of 4. 2 nuclei, 2 electrons, 2 neutrons each is 4. So what you keep releasing more and more neutrons, and if you have enough uranium around, you'll continue to split uranium atoms, and that's called a chain reaction. And that's how nuclear energy works, or how atomic bombs work, is by that chain reaction of continuing to split uranium. But you have to have enough uranium to make that happen. So if we look at that, remember that a balanced nuclear equation, the mass numbers have to balance. So on the left side of the arrow, we have 1 plus 235, which equals 236. And over on the right side of the arrow on the top line, we have 139 plus 95 plus 1, and that equals also 236. So the mass numbers balance on both sides. On the bottom, you have the atomic number. So on the left side of the arrow, it's 0 plus 92 equals 92. And on the right side, you have 56 plus 36 plus 0, which also equals 92. So that's how you balance a nuclear reaction. So in this reaction, a single neutron strikes a uranium-235 atom. The uranium-235 splits into barium-139 and krypton-95 in a process called fission. 2 free neutrons are produced. If there's enough U-235 in the area, these neutrons will split 2 more atoms in a chain reaction. It'll continue on and on. Also, 200 million electron volts of energy are produced. That's a very tiny amount, but if you have massive numbers of uranium atoms, it adds up. Obviously, that's how atomic bombs work. So this is mass converted to energy by Einstein's equation, E equals mc squared. A loss of mass occurs only in nuclear reactions. In regular chemistry, we talk about conservation of mass. You have just as much mass, just as many grams before a reaction takes place as after a reaction takes place. But you can actually have mass being converted into energy in a nuclear reaction. That's the only circumstance. Okay, the other type is just the opposite. It's called nuclear fusion. The word fuse means to put two things together. So nuclear fusion is when hydrogen atoms combine to form a helium atom. As with fission reactions, fusion reactions produce energy. So what you have is you have 2 hydrogen atoms over there on the left, and they smash together to create a helium atom over on the right, plus a neutron goes flying out into space. So in this reaction, 2 hydrogen atoms, each with 1 proton and 1 neutron. Now that's unusual. Typically we talk about hydrogen as having a proton in the nucleus and an electron flying around on the outside. But this one actually has a proton and a neutron in the nucleus. That's a fairly rare isotope. So this isotope of hydrogen is called deuterium. So it's H2. And that collides, and they collide to produce a helium with 2 protons and 1 neutron. And then a neutron is released along with some energy. So both chemical and nuclear reactions do 2 things. They cause changes in energy, and they can be represented by balanced equations. So again, both nuclear fusion and nuclear fission produce energy. Fusion, this type of reaction here, is how the sun produces energy, by smashing hydrogens into each other to form heliums. That's how the sun and other stars produce energy. Whereas the conventional nuclear power that we use here on Earth in nuclear power plants is nuclear fission. It's splitting atoms. They're trying to develop means of creating energy through nuclear fusion. They say that if they can do that, you could actually create energy from water. You could just get water out of the ocean and create energy, and that would be kind of a dream come true, to have all the energy that we need. But they haven't gotten there yet, and who knows whether they'll ever get there. All right, so that takes care of this brief lesson on nuclear reactions. There are actually going to be 3 questions on your final, and the answers and how to answer those are all in this video. So be sure you understand these concepts. And that's it. We'll move on to a new subject next week. All right. Have a good day, and we'll see you in class.